In this video, we're going to talk about the factor theorem. The factor theorem is like a shortcut for factoring polynomials and can be a really great problem-solving tool. So first of all, why is it so important to factor polynomials? So if we had a polynomial like y is equal to x squared plus 5x plus 4, if this was given to us, hopefully we already know that this is a quadratic equation and its graph looks like a parabola. What information do we have just from looking at this? Well, there's a positive leading coefficient here, kind of like a little invisible positive 1. That tells us it opens up like the letter U. And the y-intercept is clear right here because if we sub in 0 for the x value, the first two terms disappear and we're left just with y. So we have x value of 0, y value of 4. That means the y-intercept is 4. So we know the y-intercept is 4. And it opens up. It doesn't really tell us very much about the graph, does it? The graph could maybe go like this. It could go like this, so it just touches. It could maybe be on the other side, maybe go way down. We don't really know just from the graph in this form, but if we just take a moment and factor it, like this, let's see here. Multiply to 4, add to 5, well, 4 and 1, multiply to 4, and add to 5. So now it's factored. What's so great about factored form? What does that tell us? Well, if we want to solve for the x-intercepts, whenever we're crossing the x-axis, the y value is equal to 0. So x plus 4 is equal to 0, or x plus 1 is equal to 0. From factored form, it's very easy to solve. And from factored form, we can see the x-intercepts. So we can see that it would go through something like this, -1, -4, and that was a pretty good estimate for the graph. So we can get a sense of the graph very quickly when it's in factored form. It's not always so easy to factor though. Once we get to a trinomial, a cubic like x to the power of 3 plus x squared minus 2x minus 2. Just looking at this, it's not so easy to factor. If you remember factoring by grouping, this one just happens to work by factoring by grouping though. If it didn't, we'd be pretty stuck, wouldn't we? So let's do factoring by grouping. X squared Okay, so now we have it factored. It almost looks like differences squared for the first choice here, except it's -2, which isn't a perfect square. So we can't really go any further. If you're trying to solve for the roots though, you could set x squared minus 2 equal to 0, move that 2 over, take the square root of both sides, plus or minus square root of root 2. So you would be able to see the roots there. Okay. So hopefully you're convinced that factored form is a very useful form for a polynomial equation. I want you to notice that when we have the equation in factored form, if we sub in one of the x-intercepts, it works out to 0. So we come down to this cubic here, and I'll rewrite it. So we have y is equal to x squared minus 2x plus 1. And let's practice using function notation. It's really helpful so we can see what the input is. So if we put in for x one of the x-intercepts, like here an x-intercept is -1, f at -1, we get -1 plus 1, which is 0. So this whole thing ends up being equal to 0. In general, this is always true. If we sub an x-intercept in, it'll always give us 0. Why does that make sense? Why does that work? So think about this. If I gave you a polynomial in factored form, f at x is equal to, and just write it in a nice general way. Say this is a root, that's a root. So from this, we know that the x-intercepts would be positive s, positive t, positive m, and positive n. And notice that if I sub any of these into the equation, it would give us 0. So let's try that. Which one should we try? Let's put in m. M minus s, m minus t, m minus m, m minus n. Okay, so we put this x-intercept into the equation, and this gives us 0. So now we have f at m is equal to all this stuff times 0 anything times 0 equals 0. So f at one of the x-intercepts is equal to 0. This would be true for any of the roots. So this gives us a really nice theorem. The factor theorem. So if ax plus b is a factor of a polynomial function f at x, if and only if f at negative b over a is equal to 0. Okay, this looks a little bit more complicated. The more simpler version of it is, just like we saw before, if x, we had it like this, x minus m, maybe I'll pull that down below so you can still see it. So we had x minus m is a factor. It was a factor right here. And we saw that f at m was equal to 0. If and only if, this thing here just is read if and only if f at m is equal to 0. This all just means if something's a factor, then that x-intercept that you read, if you plug it in, you get 0. Okay? It's just very sensible. It relates to it being an x-intercept. An x-intercept happens when the y value of the function is equal to 0. Okay, so how do we use this? So we have a function here. If 2x plus 1 is a factor of this function, then when we sub back in the x-intercept, it should give us 0, right? That's the idea here. So this wasn't completely done being factored. We're not really concerned with the other factor right now. 2x plus 1, if this was set equal to 0 and we were solving, then we would get x is equal to negative 1 over 2. So that's our x-intercept. Let's sub it into the function. F at negative 1 over 2. Why did I choose one with fractions? Now we've got to be very careful. So what we're doing here is we're going to see if f at negative 1 over 2 is equal to 0. If it is, then 2x plus 1 is definitely a factor. So we're trying to figure out whether or not that's a factor. Okay, so 1 over 4. Okay, 2 times 1/4, 2 over 4, just 1 over 2, minus 7 over 2. Let's just put everything over 2, save some time. 3 over 1 is 6 over 2. Okay, 1/2 minus 7/2 plus 6/2. I'm going to do the minus 7 plus 6 so I don't have such difficult numbers to work with, minus 1. So we have 1/2 minus 1/2 is equal to 0. Okay, so since f at negative 1 over 2 is equal to 0, we can say that two x plus 1 is a factor of f at x. What are some other things that we could do from here? So if you look at this and if you try to figure out, well, what are possible values that could work for factors? 1 times something has to equal 3. This is probably going to be 3. We could check to see, we know right now how to factor this. So what can you tell me about f at negative 3? F at negative 3, since this is a factor, f at negative 3 has to equal 0. So the factor theorem is often very helpful when you're asked a question like, is this a factor of a polynomial? So let's just make up a question. Is 3x plus 2 a factor of f at x is equal to 3x cubed plus 4x plus 4. Is it a factor? If it's a factor, then we would have to have f at negative 2 over 3 to equal 0. Now, it's easy to flip things around. I sometimes do it. To be safe, if you take what you think is a factor and write out the steps to find the x-intercept. Okay. Did it right in my head. Never hurts to write it out. Okay, so back to this. We're trying to show that this is equal to what? Equal to 0. And I did it again, fractions. Okay. Fractions are still better than decimals. Okay, so try working this out also on paper so you can make sure that you can do it on your own when you need to. Okay, looks like we're going to need a common denominator of 9. Multiply the top and the bottom by 3. So negative 8 times 3, negative 24, plus 4 over base 9, so we'd have to multiply 4 by 9, which is 36. Okay, minus 8 minus 24, minus 32, plus 36. So we get 4 over 9. So when we put in what we thought was an x-intercept, we didn't get 0. So it's not an x-intercept, so this is not a factor. Therefore, 3x plus 2 is not a factor. And it's possible that this function might not even have a nice perfect number for an x-intercept or for a factor. It might be a really awful decimal number that we couldn't possibly guess to put in here. But it's still a very useful tool to test and try to figure out if something is a factor or an x-intercept.